Welcome everyone to the AMS Josiah Willard Gibbs Lecture. My name is Ms. Charney and I am President of the American Mathematical Society, and I will be introducing and moderating this talk. Before we get started, let me note that this lecture is in webinar format, so only the speaker and moderators can be seen or heard. We should have some time for questions at the end of the talk, so if you do have a question for the speaker, please use the Q&A button on your Zoom screen, not the chat. I will read out questions from the Q&A at the end of the talk. The goal of the Gibbs Lectureship is to increase awareness of the contributions that mathematics is making to present-day thinking and to modern civilization. Established in 1923 by the AMS Council, it is one of the oldest and most distinguished of the AMS lectureships. This year, we are very pleased to welcome Eitan Tadmor as our Gibbs lecturer. Professor Tadmor is a distinguished university professor at the University of Maryland. He received his PhD from Tel Aviv University in 1978 and held faculty positions at Caltech, Tel Aviv University, and UCLA. While at UCLA, he was also a founding co-director of IPAM, the NSF Institute for Pure and Applied Mathematics. Then in 2002, he was recruited by the University of Maryland to lead the Center for Scientific Computation and Mathematical Modeling. Professor Tadmor is known for his original contributions to applied and numerical analysis with applications to fluid dynamics, image processing, and collective dynamics. He has done fundamental work in the theory and computation of nonlinear partial differential equations, drawing on the interplay between analytic theory and computational algorithms. He has received many honors and awards for his research contributions, including an invited lecture at the 2002 International Congress of Mathematics and a plenary address at the 2019 International Congress on Industrial and Applied Mathematics. He is a fellow of both the AMS and of SIAM, and this year he was awarded the prestigious AMS SIAM Norbert Wiener Prize in Applied Mathematics. We are honored to have Professor Tadmor as our Gibbs lecturer this year. His talk today is entitled Emergent Behavior in Collective Dynamics. Please welcome Professor Eitan Tadmor.
Thank you very much, Ruth. Thank you for the introduction, and I thank the AMS. It's a distinct honor and a pleasure to deliver this year the Gibbs lecture, even though it's online. And I would like to use this opportunity to thank all of you for actually joining me here, and also to start by thanking my several collaborators that will be mentioned throughout the talk. Since the hour is late, at least for some of us on the East Coast, this talk will be on the easy side. I will include only a couple of theorems and a corollary. There will be no proofs, but I will try to share with you recent work in the last decade or so about emergent behavior and the mathematics of swarming and collective dynamics. So let me start by sharing the screen. So let me start with the discussion of emergent behavior in collective dynamics. I guess a good starting point, give me just 1 second, a good starting point for collective dynamics will be canonical examples of flocking of birds. So here are a couple of examples for emergent behaviors. I attribute this to members of the collective behavior in biological systems in Italy. And these are examples of starlings and midgets. So these are pretty standard examples for what we encounter when we think about collective dynamics of birds, and in this case, midgets. But in fact, these examples are applied to a much greater variety. And here is a list of other examples of emergent behavior in collective dynamics of living agents. So I'm not just talking about flocking of birds or school of fish or herds. You can think even on the completely different scale, the aggregation of cells which form tissues. It's not just about living agents. Another set of examples come from thinking agents, the dynamics of pedestrians, traffic jams, the dynamics of opinions, neural networks. Again, the main aspect here is dynamics at the human scale. And then still different, but included in my talk are non-living agents, sensor-based robots, UAVs, synchronized motors, and so forth and so on. So when I talk about collective dynamics, I refer to this ensemble of different examples from different corners of science. And the main question is, what are the fundamental aspects of this collective dynamics? So let me elaborate. What we are discussing is a crowd of so-called agents, which are driven by different rules of pairwise interactions. These interactions come under the name of alignment or synchronization, attraction, repulsion, but I emphasize there are no collisions. So these are not particles, but they are called agents because typically these agents actively, they have sensors or sensors with which they actively probe the environments, hence they're sometimes called active matter. So there are no particles. The other aspect is that the interaction is essentially local. These are short-range interactions. So we have to come up with some notion of neighborhood. And these local interactions lead to coherent structure that emerge as time goes on for large crowds. What are these emerging quantities? Well, we call them flocks or swarms. They could be colonies of cells or parties of opinions, or maybe we reach a consensus, but something is emerging from the local interactions. And these things that emerge, they have global effects. There's a formation of long-range structures or patterns. And this interplay between the local and the global, this is the main feature of the emerging behavior that I'm discussing. So the emerging behavior, as we can see here, usually refers to the fundamental question: how come that short-range interactions are self-organized into long-range higher-order patterns? After all, these birds that we see here, of course, they do not see the whole crowd, the whole flock, they just see the neighbors and they interact with the neighbors. And these local interactions form what we see here as a long range or higher order patterns. So this is the background that I'm discussing. In order to discuss this in mathematical terms, I will devote the whole lecture to one and only one paradigm, a model that is described in this slide for pairwise interaction. So this is a deceivingly simple model, and I will try to convince you that this deceivingly simple model covers a remarkable range of different phenomena. So what is the model? We have n agents, birds, opinions, and other examples that I will elaborate soon. Each agent is identified with a position or properties or traits, which is a vector depending on time. An agent indexed with an I is governed by this simple statement, which says that the rate of change of the position, generalized sense of position of an agent, is given by a sum, a weighted sum of the difference between the position of this agent and its neighbors. So what are the characteristics of this model? Well, the components are that we have a crowd. Each item of the crowd is characterized by a certain trait or a position, which is a vector, let's say. We have tau as a scaling parameter. And most importantly, we have pairwise interactions. So agent we index here with I interact with all the other agents, which are indexed here with J, and the interaction occurs in this coefficient phi ij. The phi ij is a function of the two interacting positions, pi and pj. So there is some function, which I will call from now on a communication kernel, which really holds the key for the model. In order for this interaction to take place, every agent, of course, interacts only with neighbors. What are the neighbors? The neighborhood are, in fact, all the agents such that this phi ij is different from 0. So again, the notion of neighborhood depends on the communication kernels, and examples will follow. And this description of so-called active matter is essentially a steering towards environmental averaging. So this is the buzzword, the keyword, environmental averaging. In order to convince you that this paradigm is relevant, I will now appeal to 6 canonical examples, which I collected from different corners of different scientific disciplines. Let me start with the first simplest example in social science. This is an example in opinion dynamics. It is so simple that it is deceivingly too simple, but it's actually much more complicated. So in this case, we have a state of opinions. The opinions are scalar. Let's say the opinions range between 0 and 10. And I'm describing here the bounded confidence model of Krause and Hexelman from the beginning of the 2000s. And the statement is that every person changes its opinion by taking a weighted average of all the other opinions which are sufficiently close to its own. So here we measure all the other opinions which say their value is not more than 1. And therefore, there are certain number of neighbors, let's call them Ni. We average with Ni, and this averaging statement gives us the new opinion later on. This is the rate of change of our opinion. In fact, it fits the model I just mentioned you, where the communication kernel or the communication function is nothing just by the characteristic function of the interval 0, 1. We interact only with those items or agents that their opinion is at most value 1 away from us. This is how it looks when we actually simulate that. What you see here over time, there is a distribution of opinion from 0 to 10. As you can see, all these agents, they communicate with the neighbors pretty well. But as time goes on, they congregate into 4 separate distinct groups, or if you would like parties. Clearly there is no emerging consensus, but what emerges are 4 parties. And in this case, the interaction is compactly supported. It's just the support of the interval 0, 1. So this is the first example of opinion dynamics. The second example has to do with, if you like, pedestrian or sensor-based motion. And now the state space is a state space of positions. So these vectors pi are actually vectors in, let's say, the 3-dimensional space. This is the dynamics of robotic agents or UAVs. And we change the position by taking a weighted average of the difference between the positions of different agents. Again, the key element is, what are these weights? Well, here are 2 examples. One, the interaction depends on the distance. So agent at position xi or robot at position xi takes into account the distance between itself and the other robots. Another model will say that the interaction does not depend on the distance, but it depends on the crowdedness. That's very fitting in, let's say, pedestrian dynamics. The dynamics is not driven by simply by the distance, by how crowded is some control region between xi and xj, agent I and agent j. Well, in this case, one canonical question is coming together. Is it true that over time, all the agents come into the same place at the same time? In general, the answer is no, as you can see here. So we start with some configuration initially, and you can see that eventually you get certain groups for this communication kernel. I can tell you that if we change the communication kernel to be 1 over r, which essentially means that we react just to the orientation and not to the distance, then in general, the answer is yes, we always get finite time gathering. This is the so-called rendezvous problem. Let me move to a completely different example. This is a question of rating. Now, the state space of rating, I will denote the rating by a scalar q, and I'm describing here the ELO rating model. Arpad ELO was a physicist and a pretty good chess player who was interested in rating different chess players. This was in the 80s, and his model goes as follows. It's based on a zero-sum game with random outcome. So 2 players, I and J, play, and they change their rating by either gaining the difference in the rating between player I and J, or losing according to the difference in the rating. And of course, it depends on the random outcome Sij. Of course, Sij plus Sji should be 0 because it's a zero-sum game. So one loses, other gains, or vice versa. And then each player plays against, let's say, all the other players. It's slightly more delicate here, so I denoted here by this kind of symbol, but essentially it delivers the message that there is a game here. This is the kind of interaction. And of course, now it depends on the function phi, which is a function of the difference of the ratings. Now, what is the expected value of the game? The expected value of the game between two players I and J should reflect somehow the difference of their intrinsic strengths. So we will denote the intrinsic strengths by rho, not by Q, and we expect that the expected values of the outcome will reflect this intrinsic strength. This kind of rating today is adopted by chess players, FIFA, table tennis, and many others. In fact, the Chess Federation is using these interaction kernels. FIFA in soccer is using these interaction kernels. So, in fact, this model is taken from the ground. I should mention that the rating itself reflects intrinsic strength, so that one expects that the rating will approach the strength, which is worked out quite recently. And I noticed that in this model, every player has two characteristics. It is the rating, which is observed, and the intrinsic strength, which is unobserved. And there are learning effects, and there is more, and there is more. This brings me actually to my next example, because now we see that agents could have more than just one characteristic, namely not just rating, but rating and intrinsic strength. So the next example for flocking, this is the celebrated Cooker-Smale model, which was introduced in the 2007. In this case, the state space is a space of velocities. They could be in R3 or RD, and we run into the usual paradigm that the rate of change of the velocity is given by a weighted sum of the difference of the velocity between agent I and all the other agents J. The key element, the communication kernel. What is the communication kernel? The Cooker-Smale takes that the communication kernel is a function of the relative distances. So the dynamics is on the velocities, but we have to take into account the positions, the actual positions. So overall, this is a second order model, which involves the position and the velocity. So each bird, if you like, is characterized by a position and velocity, and it aligns only the velocities depending on the positions. What kind of communication kernel we have? Originally, it was introduced by Cooker-Smale. Since birds of feather flock together, we can think of a communication kernel which is decreasing as a function of the distance, because the impact decreases with the distance. Of course, there are many other questions that could be asked, and I will not raise it. What about limited visibility? Shouldn't it be that communication kernel has to stop at some point and should not go all the way to infinity, and so forth and so on? Since I mentioned clocking, let me bring the fifth example. This is another celebrated model of Vikshek that is introduced earlier in 1995. And in this case, the idea was that the dynamics of birds is dictated by a state of space orientation. So the speed is assumed to be fixed. Each bird has orientation, and they change the orientation according to the usual rule, where we have a weighted average of the difference between its own orientation and the orientation of its neighbors. All these other notations here of the perp indicate simply that we stay on the unit sphere, so we take just a tangential change. The important thing is, in the additional to the dynamic itself, we introduce here a noise with amplitude which is proportional to square root d. Here's an example for the communication kernel that was used in the Vikshek model. It's a characteristic function of a ball, let's say radius less than 1, but it's finite. So here are the positions that are dictated by the orientation and the fixed speed s. Altogether, it forms the velocity. So the only thing that we change is the orientation, and we will see an example for that later on. The important factor here is the noise. If we have a small amplitude for the noise, then we do get global alignment. If we have increasing size of the noise, we get homogeneous disorder, and there is a lot of discussion in the physics literature of the phase transition going from one to the other. I will not elaborate. I should mention, I debated whom to quote here, but I would like to single out at least two examples, canonical examples, for people working along these lines using the swarming model for Vic-Check. One is the lab of Ian Cousin, the lab for collective behavior in Max Planck Institute in Constance, where you can see a lot of simulations and more important, even actual experiments which have to do with birds, with locusts, with fish, and many more things. And I already mentioned the group in Italy, the COPS, with simulations and experiments with starlings and the midgets. And in particular, let me mention the Starflag project in 2008. This was a famous project trying to understand the dynamics, the collective dynamics of birds, of starlings. So this was the fifth example, which brings me to the sixth and the last example of synchronization. In synchronization, we have something completely different. The state space consists of phases. So the phases run on the unit circle. This model goes under the name of Kuramoto, but before it goes to Winfrey, and even before it goes to Norbert Wiener. This gives me an opportunity to, I believe that in the crowd, there is at least one person that I must mention. Earlier this year, I received the Wiener Prize, and among the many congratulations, there was something very special. There was a person that congratulated me who actually met Norbert Wiener. So this was a live hello from Norbert Wiener to this person. So I would like to acknowledge this very special congratulations. So hello, Sid Shapiro, if you're in the audience. So the Kuramoto model is given here. We change the phase in the following sense. We take an average of the sign of the difference of the phases, and each agent has its own intrinsic frequency. So there's a tension here between averaging the information with the neighbors and the own characteristic of each agent, omega I. So these are random numbers, and they're assumed to have a zero average. Of course, it fits our model because now the phi ij are simply the ratio between the sign and the difference of the thetas. They're not always positive. It's slightly more complicated, but it fits the general paradigm of alignment. And indeed, when we want to study that, we have to look at phase coherence. One introduced this quantity R for phase coherence, which takes basically the exponential average here. And there are two extreme cases. When R is close to zero, it means that there is equidistribution, there is no locking, there is no coherence. And when R is close to one, it means that all the thetas align in a certain direction, and we get the synchronization, the case of synchronization. And what we see here is that there is a tension between the intrinsic frequency and the alignment. So if the amplitude of the alignment tau, k, is increasing, then we put more alignment, and you can see this is a nice simulation. You can see that when k equal to 1, growing to 6, and going to 12, you can see here that there is no locking, there is partial phase locking, and here there is full locking because the alignment wins. So this concludes my 6 examples, different examples for the basic and the only one paradigm that I will share with you in this talk. And this is the paradigm of alignment. So I repeat the alignment dynamics. We have agents with positions in the generalized sense given here, and each agent changes its position by taking a weighted average of the different positions between itself and the others. And the key element is this communication kernel. Different communication kernels appear in different contexts depending on this function phi. So the dynamics is dictated by phi, and so is the neighborhood. Okay. So the question is, where does this communication kernel coming from? There is no Newton law here. The source of the communication kernel, they come from different sources. Here's a busy slide that will try to convince you that they come from different places. One example are phenomenological kernels, where the kernel is simply a function of the distance, and I mentioned a few examples. It makes sense that we take a metric kernels which depends on the metric distance. And here are different examples in Kruker-Smale, Risk kernel, and so forth and so on. Another source for these communication kernels are observations. For example, topological kernels, which I already mentioned, they were experimentally found, for example, in the Starling project, And here I mentioned another name of Parisi because he received this year a Nobel Prize in Physics. And they found that the starlings, as well as the dynamics of human crowds, pedestrian, is in fact dictated by topological kernels. That is the crowdedness between two agents rather than the distance. Another source for such communication kernels are random-based. I already mentioned the ELO rating, phototaxes, and so forth and so on. Another source, these kernels are learned from the data, and I mentioned here a few examples, but there are more. And last but not least, there are higher order principles. One can derive the notion of communication kernel from higher order principles. Here are two examples, a minimum entropy principle that I will not describe, and anticipation. So let me move now to describe the notion of anticipation. So anticipation and tree-zone model. Let me start with a model for anticipation, and I would like to share with you how anticipation breeds alignments. So I start with a discrete model depending on the position, x, and the velocity I. So each agent has positions and velocities, and the velocities are driven by the gradient of some potential. We will talk later on about that potential. The important thing is that in these dynamics, the potential is evaluated not at the difference of positions, but the positions are the anticipated position. What are these anticipated positions? These are the positions which are anticipated, not at time t, but at time t plus tau. If you like, this is the counterbalance for systems with delay. In fact, we know that anticipation is a viable option in social dynamics for living organisms, mean field games, robots, and so on. Now, what is the role of this anticipation? Let's take the term on the right, whatever it means, and let's expand for small tau. So the first term is given here, and it's simply the gradient of u. You don't see the tau. This is when tau equal to 0. And this term represents repulsion and attraction. I didn't discuss so far repulsion and attraction. The next term, when we expand in small tau, gives us exactly the model that we are discussing all along, namely that the rate of change of the velocity has to do with alignments of velocity. And what is the phi? The phi in this case has to do with a matrix with the Hessian of this potential. If you take the scalar version of that, then we literally derived the model of Hooker and Smale. So what we learn from this example is when tau equal to 0, what we have above is precisely the canonical classical n-body problem. When we take the n-body problem with anticipation, we get an extra term which represent alignment. So we get repulsion and attraction, which are familiar to us, and additional term of anticipation. Altogether, we get a tree-zone model, which involves the repulsion, the attraction, and the alignment. And in fact, this is described here. What are the potential? Well, we can take the Lennard-Jones potential or Morse potential. So essentially, we get something of this nature. And in the decreasing part, it's the repulsion. The increasing part is the attraction. And in between, we have the alignment. And this represents the three zones that each agent, in this case, it's a fish, feels. The nearby neighborhood is a region of repulsion. Don't get too close to me. In between is a region of alignment, and outside there is a cohesion so that we stick together. This three-zone model was introduced by Craig Reynolds in 1987. So let me tell you a little bit about Craig Reynolds that introduced this model in 1987. The idea for Craig Reynolds, he wanted to make realistic simulation for birds, for flocking of birds. So he postulated three rules: the rules of repulsion, attraction, and alignment in between. And this is essentially the model I described to you so far. Now, repulsion and attractions are familiar from particle dynamics. The key new feature is alignment. This is what I'm discussing this evening. In order to convince you that alignment is really important, here is a simulation for realistic description of BOIDs. BOIDs stands for birds-like object, as coined by Craig Reynolds. And what you see in this simulation is the interaction of BOIDs. They are subject to repulsion, so there is no collisions. They stick together. This is the attraction. And most important, the alignment keep them aligned so you get something which is very realistic to a flocking of birds. The key feature here is the alignment, and that's what I'm focusing this evening. In order to show you that this is a key feature, look what happens when we just turn off the alignment. Still, there are no collisions, there is a cohesion, but there is no order. So it is the three of them that make a viable model for collective behavior. Indeed, Craig Reynolds received for this model the 1998 Academy Oscar for technical, recognizing the technical achievement here. And I should mention that the three-zone model is still, to date, there is still no mathematical theory, in particular to the local aspect of the three-zone model. Okay. So what would I would like to ask about our model for alignment dynamics? We know that the dynamics is dictated by a communication kernel. There is a large class of communication kernels, and they dictate completely different behavior in completely different contexts. So the question I would like to raise is the following: how different classes of kernels, communication kernels, affect the emergent behavior? So this is the single question I will devote the rest of the lecture to. So let's talk about short versus long-range interactions. So we get a little bit into the mathematics here. So this is, again, the basic model. This is the communication kernel. What we see here is a graph. The graph essentially consists of edges. Edges are all those pairs of agents which communicate. So the communication is positive. The other the other pairs do not communicate. And of course, there are vertices. So there are edges and vertices. There is a graph. And we would like to see what is the large time behavior for this model. And in order to study the large time behavior, I will introduce the energy fluctuations. The energy fluctuations takes into account all the differences squared of all the agents in this ensemble. So we define these energy fluctuations, and the following statement is true. The rate of change of the energy fluctuations equals the quantity that is written here, and this is less equal than the quantity written on the right-hand side. Let me elaborate. So I copied the same thing, energy fluctuations, and I copied the same statement, 1 and 2. Let me tell you something about 1. Why there is equality here? There is equality because I assume that the interaction between two agents is symmetric. Phi ij is equal to phi ji. And in this symmetric case, it turns out that this quantity is antisymmetric. And in this case, it follows that indeed the rate of change of the energy fluctuation is given by this quantity, which is called entropy. You should see that this is a negative quantity. The question is how negative it is. I want to quantify how negative it is because it will tell me that the fluctuation decay, and if fluctuation decay, it means that the large time behavior flock or approach or get into consensus as t tends to infinity. So how negative it is, so we have this inequality, and this is a sharp inequality, where this red quantity, which multiply the energy fluctuation, this red quantity is given by the second eigenvalue of the graph Laplacian. I wrote it here. This is not that important. What is really important is that this spectral gap or second eigenvalue completely characterize the decay rate of this complicated term here, so-called the entropy. So what is the conclusion? We can integrate this differential equation. The rate of change of the energy fluctuation is less equal than minus 2 tau, this coefficient, times itself. And when we integrate, we get the exponential of the integral in time of the spectral gap or the second eigenvalue. Therefore, the energy fluctuation will tend to 0, and we will get unconditional flocking because then all the positions will approach a limiting case, if and only if the second eigenvalue is not only positive, but its integral tends to infinity. Then this exponent will tend to 0. And this thing reflects the fact that the graph needs to be connected. Connected in the sense that every agent, every node has to be in communication with every other node, maybe through intermediaries. So here are a couple of examples for long-range kernels. This is the alignment dynamics of Cooker and Smale. It turns out that one can bound the spectral gap in this fashion, depending on the diagonal of the communication kernel. And if our kernel has a heavy tail, so it decays, but not too fast, then we get unconditional flocking. If we have alignment and attraction, the same story. If we have heavy tail, which is quantified here, the key word is heavy tail, then we get unconditional flocking. If we have repulsion, the problem is largely open. So this is if we have long tails, but what happens if we have short tail? If you remember, I studied in opinion dynamics, this is the example of having a short tail, and indeed, we did not get consensus, we get 4 parties. On the other hand, if I take another short kernel, I change it slightly, and I make it actually increasing, then we get consensus. So you can see that by changing a short tail kernel, actually compactly supported kernel, I get completely different behavior. And the reason for that is that this discrete dynamics is inherently with the short tail unstable. So there is an issue of instability here. And if we want to control the diameter of the flock or the group and to get the alignment so that the velocities will tend to 0, there is a very delicate balance here between the dynamics of the graph, the spectral properties of the graph, the dynamics on the graph, and this feedback actually can lead into a situation that the connectivity of the graph breaks down. That's exactly what happens in the previous examples, and we get clusters rather than flocking or consensus. So there is instability for short-range phis, and in order to address this question, we would like to study the case of large crowds. So instead of taking finite n, I would like now to take n, which is much larger. And this brings me to the last topic of this lecture, large crowds hydrodynamics of emergent behavior. Now, why large crowds? Actually, it goes back to Immanuel Kant, who said in 1784 that what seems complex and chaotic in a single individual may be seen from the standpoint of the human race as a steady evolution. I like this quotation because it tells me that large crowds stabilize. So how do we study the large crowds? There is something which is called empirical distribution, which is not important at this late hour, but what is important is that we study the large crowd in terms of the density and momentum. For those who are not familiar, I think the following simulation of Sebastian Moch, is very revealing. This is simulation of the Vic-Shack dynamics. So what you will see on the left is the Vic-Shack dynamics. What you will see on the right is the large crowd dynamics. So here are the details of the Vic-Shack with I don't know how many particles or agents. We are really not interested in all these details. What we are really interested in, and you can see, we're interested in the density. You can see the change in the density according to the intensity of the color, and we can see the direction of the momentum. So essentially, the density and the momentum capture macroscopically the detailed information that we are not interested in here. And this is the language that I would like to discuss now, the emergent behavior and the collective dynamics, the language of hydrodynamic description. So this hydrodynamic description in terms of density and momentum is described here. We have an equation, now we're talking about PDE, an equation for the mass. This is a canonical mass equation. And we have a momentum equation for the velocity. And the momentum equation involves two components. One is the alignment. What is the alignment? Is a term which is written here. It involves the communication kernel, and it tells us that a collection of agents, but in a continuum sense, with velocity u at position x, takes into account all the other positions at position x prime. We integrate over all other positions with this density, with this communication kernel, and we get the alignment. There is also a pressure term, which is a bit mysterious. This is not a purely hydrodynamic description because we need to close the pressure, which I will not do at this late hour. And in particular, I will mention the quotation from Vic-Shack, who said that the source of energy making the motion, collective motion, possible is not relevant. I agree to a certain degree. I agree that the closure equalities can be substituted with inequalities. So I will not discuss now the notion of a pressure. So if in the discrete case, we look at the discrete energy fluctuations, in the continuum, this is the definition of the energy fluctuation. It's given here. This is the continuum analog of the discrete terms that we have there. It involves the fluctuation of the macroscopic velocity and the internal energy, which has to do with the trace of the pressure. Essentially, it's microscopic fluctuations. So this is the energy fluctuations, and you guessed it right. We look at the rate of change of the energy fluctuations, and there are two terms, two steps, 1 and 2. Step 1 holds simply because the communication kernel is symmetric, and step 2 also holds with some spectral gap of another weighted Laplacian operator. If you're interested, this is the operator, but we will not get into the details. The important thing is that there is a spectral gap here, and here's my first theorem at 8:45 p.m. The theorem says that if we have strong solution and the density is bounded away from vacuum, with some mesoscopic pressure, then the fluctuation of the energy will decay, dictated by the spectral gap of this mysterious Laplacian. So we have to study this second eigenvalue of spectral gap, and that's what we do now in the case of long-range interactions. So what is long-range interactions? We assume that we have heavy tail of order beta, which essentially means that there is propagation of information. Every agent is in contact with every other agent. So here's the long-range communication that I'm discussing, and the spectral gap is bounded from below by the difference of x minus x prime. And now we have to see what happens with the diameter of our crowd. You see, when you have a crowd, the crowd may disperse, and the dispersion here is quantified by some power gamma as time goes on. And there's competition by the decay beta and the growth of gamma. In fact, when we plug one into the other, we see that it's their product which matters. Namely, their product should be less equal than 1. So the conclusion is that if gamma, the rate at which things sort of disperse, is not too fast, then the fluctuation and the internal energy and everything goes into flocking, they go to 0. So the question is about the dispersion of the crowd. We have to have a crowd. We have to talk about a cohesive crowd that we will say, call it a flock. Here is a series of examples. If there is no pressure and if beta is less equal than 1, then there is unconditional flocking. If there is a matrix communication kernel and beta is less than 2/3, then there is unconditional flocking. If we take the one-dimensional case with any pressure, with singular head, then with this range of parameters, then there's unconditional flocking. Of course, there are many works in this direction. I do not cover everything. I just want to give a sense, a taste of the results that are going on. So this is a summary of the long-range interactions. Of course, what we are interested are the short-range interaction. But before I come to short-range interaction, here's another example of external forcing. It's not only that we interact with the environment also affects the dynamics. So here is an external forcing. In this case, there are energy fluctuations, they decay. And if you take, for example, the case of a harmonic oscillator, the dynamics looks like this. So what you see here is the crowd focusing both with the velocity and the position around this harmonic oscillator, and they come together. Okay, all these cases fall under the category of long-range interactions. What I'm really interested are short-range interactions. Well, short-range interactions are really the models that we are interested, but the result in these directions are in short supply. There are several results, but our understanding is still incomplete. I would like to conclude with just one example. The example has to do with the fact that the information does not propagate directly between every two pieces of the dynamics, but through a sliding average. And here's the example. We consider the case that we have topological distance. So between two positions, x and x prime, or x and y, we take into account the mass in some control volume omega, or c. I denote this quantity by mu. This is the total mass. This is the crowdedness between x and y, or x and x prime. So this is the crowdedness. Now I take a short-range protocol. Pay attention that I take a short-range protocol. So my communication is the characteristic function of all the agents which their distance does not exceed 1. So it does not cover the whole configuration. It's really short range. It's cutoff. And then we divide by the crowdedness or the total mass. So the communication is inversely proportional to crowdedness. And we call it topological distance. Why topological? Because in the discrete case, it essentially means that the dependence is not on the distance, but on the nearest neighbors. We just see the nearest neighbors, but not beyond. Well, with this configuration, this is the usual description that I mentioned before, but with this phi, which is holding the key to the dynamics here, here's the second and last theorem. It says that with these short-range topological kernels, smooth, non-vacuous solutions, if the density is bounded away in this fashion from a vacuum, then the dynamics must flow. So this is just one example for short-range interactions. There are a few other examples, and this is a very active area, which is an active research area these days. Let me conclude now with an overview of collective dynamics and different questions that arise in different fields. This issue of collective dynamics, as I mentioned, arises in biology. And the question there are basically what are the rules of engagement, and in particular, whether the patterns that are observed are system-specific. Different perspective coming from physics. In this case, there are ensembles and they act similarly, and one try to classify the patterns of collective motion simply because of similarity between different ensembles. So that's a different approach than in biology. In computer science, I already mentioned that there is a point of view of viewing the dynamics as the dynamics of clustering a spectral theory of graphs. This question arises in engineering when the question of interest are control, optimization, safety, and so forth. And of course, the question that arises in for mathematical aspects, modeling. I did not mention numerical simulations, mathematical analysis of the different quantities. And of course, the tools that encountered in the different corners of science for collective dynamics are different. In biology, there is the empirical data, which is extremely important because there are no Newtonian laws in this case. So the empirical information is critical. In physics, there is the issue of order and disorder in complex systems and statistical mechanics. In computer science, there is a role of the discrete topology. In engineering, it's the essential design of features of control and synchronization, which I mentioned already. And in mathematics is the description going from agent-based to kinetic models and macroscopic models. And with this point, I will conclude and thank you for your attention. And let me use to close my talk. This is the advantage of talking about flocking. Let me use this nice video of flocking. Thank you.
Great, and thank you very much. That was extremely interesting.